Hey guys, today we'll be using the second derivative test to determine inflection points and concavity intervals. So this is just a simple second derivative problem. Let's say our function is f of x equals 6x squared minus 4x cubed. So the first step that we want to take whenever we're given this type of problem is we want to take the derivative first. So to find the first derivative, this is a polynomial, so it should be easy. We're taking the 2 here and multiplying it to 6, so it'll be 12x, and then taking the 3 and multiplying it with the 4, so it'll be minus 12x squared. And if you need a review on that, you should review the power rule of derivatives. So now that we have the first derivative, there's not much we can do about this for this problem because it's asking you for inflection points and concavity intervals. So in order to find those two things, you're going to need the second derivative. That's why they're telling you to use the second derivative test. So to find the second derivative, we just take the derivative again, but this time of the first derivative. So when you take f double prime of x, it will just be 12 minus 24x. So just as a reminder, we took the derivative of this to get f double prime of x. So now that we have the second derivative of f of x, we need to set the second derivative equal to 0. So when you do this, you need to find the critical numbers of f double prime of x, which is where f double prime of x is equal to 0 or is undefined. But in this case, since f double prime of x is just a polynomial, we do not need to worry about where it's undefined because it is defined for all real values of x. So here, when we find the critical numbers, it should just be where x is equal to 1/2. That's because when you say 12 minus 24x equals 0, then you'll get 24x equals 12, so x equals 1/2. So this is our critical number of the second derivative. Now what we're going to want to do is plot a number line. And this is just for the second derivative of f of x. So when we plot the number line of f double prime of x, we need to put this critical number value right in the center. In problems where we'll have more critical numbers, we're going to need to put all of them. But in this case, since we only have one, you just need to plot this down. So once we have this, we need to find a value and test it into the f double prime function, one that's below 1/2 and one that's above 1/2. I'm going to test the values 0 and 1. So these values, we have to plug it back into the f double prime function. So if we just evaluate f double prime of x at x equals 0, we will get a positive number, right? Because f double prime of 0 equals 12 minus 0 equals 12, right? So that's positive. So we're going to put a plus here. Now we want to evaluate f double prime of x at 1. So we know that f double prime of 1 is 12 minus 24, which is equal to negative 12. And that's a negative number. So we're going to put a minus over here. So what does this number line tell us now? Now that we've completed this number line, we can assume that since f double prime of x is positive over here and is negative over here, that means that the graph of f of x must be concave up over here and must be concave down over here. So this is a concept that you should remember whenever doing these types of problems. So now that we know that at this value, x equals 1/2, f double prime of x changes from positive to negative, we're going to want to know what is the y value of this point when we plug it back into the original function. So I'll explain to you shortly why we need to do this, but first let's just plug it in. So we want to find f of 1/2. And remember, this is plugged into the original function f because we've already completed the second derivative test. So when we find f of 1/2, we're going to get 6 times 1/4 minus 4 times 1/8. So that's equal to 3/2 minus 1/2. So that's just equal to 1. So f of 1/2 is 1. So what does this mean? Why did we find the value of f of 1/2? Well, that's because whenever the second derivative changes from positive to negative or negative to positive, basically whenever the f double prime of x changes sign, that's where the graph of f of x has a point of inflection. And remember, a point of inflection is where the graph changes from concave up to concave down, or concave down to concave up. And just think for a moment why this makes sense. This makes sense because when we look at f double prime of x, it changes from positive to negative, which means that the graph of f of x goes from concave up to concave down. And by the definition of a point of inflection, there must be one here because it changes concavity. So now we can get our final answer. We can say that the graph of f of x is concave up, and I'm just writing CC up because it's shorter to write. It's concave up on the interval -infinity to 1/2. Why? Because f double prime of x is positive from -infinity to 1/2. And f of x is concave down on the interval 1/2 to infinity. Why? Because f double prime of x is negative from 1/2 to infinity. And don't forget, you do not want to put square brackets for this type of problem. You just want to put circle brackets because we know that at the value 1/2, we did not test it. We know that it's a critical number, so it must not be included in these intervals. And finally, we can write our point of inflection. So we found that the point of inflection is at the value where x is equal to 1/2. And we know that when x is equal to 1/2 on f of x, y is 1. So we can just write this as f of 1/2 equals 1. So this is going to be our final answer. Thank you for watching.